than point to zero. So now one of the problems you can have, because memory operands can arise before all the writes are completed, as well as the fact that they arrive out of order, what happens is when the data comes into one of these, a given slot indexed by the instruction tag, so there are 16 entries in each one of these, and so a given MDR slot is 4 given the source 1 operand for an instruction. And it's conceivable that an instruction in front of the current instruction, or the data operand that's being delivered, is in fact going to stomp on that operand. And the mechanism used to try to check that is to put a cam associated with each one of these memory data registers, which contains physical address bits of the quad word. And each time when stores come in, the stores add the physical address of the store. Another reason we need the physical address of the store as opposed to the virtual address. Gets checked against that cam to see if there's any possibilities for writing one of the prefetched operands. And then if there is, it's possible with a memory data forwarding to in fact update the particular copy right here in the MDR. Now clearly if you're doing byte writes or an unaligned write on top of it, then that won't help, and so you're going to have to, a flag is going to have to get set, and E0 has to refetch the final operand. That's a very complex piece of business. One thought it would buy bags. It doesn't buy too much at all on these codes. And that's nice because now you can get rid of a lot of that complexity and go with something simple. Anything else? Of course, if you're going to do the memory data forwarding, you have to keep that, a cam on the full physical address. If you're not going to do memory data forwarding, then you can keep some partial physical address, and if you get a conflict, just do the refetch. You only need memory data forwarding or you only need the full physical address if you're going to in fact try to forward the data locally within E0. So then what E0 looks like, it gets delivered these E0 commands, each one assigned a tag, each one corresponding to a given core macro instruction. And the free slot tells it basically this is a 16 entry buffer corresponding to a number of tags. And the free slot tells you where the next available slot for extract or dump command is. Extract basically is controlling that by assigning tag. The issue pointer is controlling the current E0 command as far as E0 is concerned, and it governs basically what piece of interlock checks have all the operands arrived, are all the registers available. There's a mouse and you write the register, it'll stall until the write completes. And so each cycle is trying to check the validity codes for an E0 command, and when they all clear, it goes, and the issue pointer gets bumped. Now the retire pointer gets advanced each time an instruction pops out of the execution unit all in one piece without any problems like overflows. Or at this point, you won't have memory management problems because you've pre-checked all those things. It is possible, though, that at issue, you will have operands that have memory management problems, at which point you'll stop issuing and wait for the machine to drain, basically, wait for any issued but not retired E0 commands to complete, and at which point raise an exception or a drag.
The EBON issues instructions sequentially in order that
right.
Instruction could go ahead.
Right, and in fact, an example of maybe a benefit of issuing out of order, although usually when you try these harebrained things, they tend to buy you not much at all.
Right.
But what is, for example, when you have an address register interlock, it's conceivable that if you were willing to issue some move instruction, which is maybe pulling a pointer out of memory, out of order. If you saw, for example, that this was just a move instruction, moving a memory operand to a register, you could conceivably execute it out of order, but then you have all the problems of undoing that crap when you discover something else has gone sour. So we just said we won't do that stuff. And that's about it for the first part. Notice I am 15 minutes into the second part. I don't know, if people want to take a break or anything right now for 5 or 10 minutes and then come back, or do you want to just continue?
Keep going.
Okay, in terms of performance, this particular chart reflects the performance in ticks per instruction again. Remember early on I said the performance metric is ticks per instruction, and that the 780 is about 10. Of course, on the 780, that includes all the instructions. It also includes some complex exceptions conditions that may not be properly accounted for, probably aren't accounted for. But although we do manage the TV misses, we manage them by calling them 15 cycles of delay to resolve them, basically. Although it could be much distant. So this thing is for the basic machine, which is the machine without a lot of the features. In fact, I think that slide's out of order now that I look at it, because I should explain basic machine before I try to tell you what it's going to. Basically, these are some of the different features that we're experimenting with. Whether or not the virtual I cache is there, whether or not branch prediction is enabled, whether or not that branch target buffer is present. You can have branch prediction with or without that. Of course, you can't. We don't have branch prediction. We don't have the branch target buffer without branch prediction. Whether or not auto increment decrement specifier handling is there, and indirect specifier. Now, I guess I should mention that briefly. What happens with auto increment decrements is they're handled as far as address mode, like most other specifiers, if this feature is enabled, and 81, which does the register read, also does the increment of that contents. And of course, it has to obey the address register interlock constraint. And then what extract does when it sees one of these things is sets a few bits in the E0 command so that when E0 gets up to that E0 command ready to execute it, it makes its own local copy, own local change to its copy of the GPRs. And so basically they are kept up to date in a staggered in time when it's appropriate for their context to update. Now, if you don't have that feature enabled, then auto increment decrement specifiers get serialized. And what serialized means is the pipe drains until that's perhaps a bit severe, and you could argue that there's an in-between point where I'm not exactly sure what that would be, but you could probably devise an in-between point. So in any case, this is quite a contrast. One of the objectives of serializing completely was to see, doing the simplest thing, what would the penalty be for doing the simplest thing? And sadly, it's a bit of a penalty. Indirect specifier handling is similar in that, except that in that if it's not present, then the specifier gets serialized. If it is present, then the indirect address finally gets delivered to the E-box, E0, and E0 has to fetch the final operand when it gets up to that point. It can only do it when it gets up to that point because it has a stale data problem. Whether or not the virtual data cache is present or absent. If it's absent, you go through the main TV and the main cache. The presence or absence of the delayed specifier table, memory data forwarding, and a couple other features which we may or may not get to. Fast instruction parsing, which was to see what the effect of trying to parse more than one specifier per cycle under some constraints would buy you, and whether or not the presence of an RSB return address stack. So for the basic machine, all these things are disabled, which means there's no VIC, there's no VEC, there's no branch prediction, etc. For the enhanced machine, everything is there except for fast instruction parsing, which we don't think is realizable, and the RSB return address stack, which we decided not to include at the start because it didn't help a broad class of codes. We'll see some effects of adding the RSB stack to the enhanced machine. I think we will. And then the VB-AIK machine is just a mnemonic for both virtual caches present, branch prediction present, auto increment decrement specifier, indirect specifier handling, and an 8K cache flushing. For this class of experiments, they were all the caches, the branch prediction, branch history table, not the branch history table, but the branch target buffer. The VIC, VC, and main TB and main cache were all flushed every 5,000 instructions. Configurations for the caches and main store are there. A bank?
Yeah.
It's basically there are 8 independent memory banks, if you will, and they can all be running in parallel. You each hand them an address, and they sit there and cycle their RAMs to finally cough up the data. The bank cycle time that is selected to take 16 cycles in order for the banks to cough up their data locally. Then going to take a few more cycles to finally deliver that data to the respective data RAMs of the caches. So the point of the banks, if you had only one bank, that means once you started that bank in operation, you'd have to wait 16 cycles plus the time to discharge the data before you could start another request. So it's 8-way interleave, and there's 16 bytes per bank, so 2 quad words per bank, so that a hit of every bank plus 2 quad words per bank delivers 16 quad words, which is 128 bytes, which is the block size of the virtual iCache. But the banks are, in fact, the bank's operation is actually started serially. Okay? That is a fairly beefy memory and is undoubtedly more than one really needs, especially when one observes that the 128 bytes in the virtual iCache does not really buy you all that much incremental performance, and in fact hurts you for programs which do lots of REIs. One of the things would be useful to do is to experiment with different combinations of number of banks and bank cycle time to get a space there. So now, given enhanced and basic machine characteristics, the basic machine runs at between, 7 and about 9 ticks per instruction. 10, and what's interesting is here, 10 is on average what 7, 8 did, if you remember that graph. So I don't know, the basic machine is somewhere in this range. The enhanced machine, that is when you add all that other whizzies, you pull that down to close to 3 and a little less than 6 for some of them. Mail is among the worst. Mail has about an REI at least the mail trace we got is an REI every 70 instructions. I don't really understand why that is the case. It has a tremendous number of change mode to kernel instructions, or it was a change mode to executive, I don't remember. And so there's an REI to answer each one of those. I don't understand that, but that does not contribute to the performance of mail.
That's a big problem.
Dave, are any of those ticks overlapped in time, or are they all serial?
Maybe that's not clear. This does not refer to ticks per instruction. Is basically the number of cycles it took you to simulate a given trace divided by the number of instructions in the trace. So it's throughput, if you will, rather than the latency through the pipe. That is, every 7 or 8 or 3 cycles, an instruction is getting retired, say, out of the e-box. So that does reflect the overlap of the operation. All right, I think actually my slides are out of order, but there's a way there. And talk about the effect of one tag on the basic machine. So the basic machine has none of the features in that feature list, and further, it now has only one instruction tag. The effect of having one instruction tag is that you parse one instruction, ship it into the machine, and then you wait until that instruction completes, i.e. the e-box has retired the tag, before you can start another one. And the performance degradation on the basic machine, by having basically serializing the entire stream, is to degrade the performance from the figures it was at, the number of TPI, by from about 12 to 30%. Most of these, almost all these charts are now going to be in percent change relative to either the basic machine or the enhanced machine.
So one tag means you're essentially not getting any benefit out of any of that pipeline stuff.
Right.
You think just does one thing and insists on it.
Well, you are getting some benefit. You're getting overlap of specifier processing and operand processing,
Okay.
but you're not starting another instruction. So in fact, there is, and in fact, I think if you compute this in TPI, it is pretty much in the vicinity of 10 TPI,
Yeah.
which I thought was curious. Okay, because the RSB stack was added later, it wasn't included as part of the enhanced machine, but basically adding the RSB stack, which is basically a private stack inside extract, every time you see a BSB, VSW, or a JSB, you take the return address, and of course it gets written to the machine stack, the memory stack, but it also gets stuffed into a private stack, which is a wraparound affair, so that when you see the corresponding RSB instruction, you pull it off this internal stack. And of course, if you're wrong, then that's equivalent basically to a branch prediction failure. But in any case, having that improved performance of the enhanced machine, adding that on top of the enhanced machine by not too much. It varied from about 0 to less than 5% for most of them, and then sort. As I said, the portion of sort turned out to be a few hundred instruction loop. It benefited quite a bit. One of the reasons that benefit's going to occur is that for people doing JSB or BSB, RSB subroutine linkages, that usually means they're managing their own stack frames, and usually the last thing they do before they do the RSB is to bump the stack pointer, at which point now you've got to wait for that add instruction to go through the machine, update the GPR before you can read the stack pointer for the RSB instruction. Or rather, before you can use the stack pointer to compute the return address, to fetch the return address for the RSB instruction. And so DEXIM and sort, DEXIM does that quite a bit, but it's apparently not as frequent as sort, and sort does it up the kazoo. Now, one compiler way to manage that would be to have the compiler adjust that stack pointer earlier before it gets the RSB, so thereby not putting it right behind it. I don't know how practical that is in most situations. I suspect it's probably not too difficult to do. All right, this is the effect of that delayed specifier table I was talking about, which if you have an address register interlock in AD1, you set the specifier aside so you can process other specifiers behind it, and then finally when the write completes to the register, the specifier is processed. And as we see, the glorious bags of performance that has brought us from 0 to 6 or 7%. And so this is a fine example of a negative result. I suspect it's really, in some sense, a negative result because we don't really do instructions out of order. At some point, we're going to get down into the e-box and we'll be sitting there waiting for that operand to arrive, which the previous instruction is undoubtedly going to make available to you by unlocking the register. And so even though you may have fetched other specifiers behind it, it hasn't done you a lot of good. You're still basically going to be serialized for that instruction. So not having that means now that memory operands are kept in order, and the complexity of the delayed specifier table disappears. And this is another piece of complexity which disappears. Memory data forwarding. If you run the enhanced machine, which has all the options enabled, and then you disable memory data forwarding and see what the performance loss is by not having it, this is a performance reduction percentage. It varies for male, from 0% to 4 and a fraction for chariot. And so this is another good negative result because now it gets rid of a lot of complexity that you might have wanted. Now, in fact, this result may turn out to be somewhat different if you run a lot of Fortran loop style things for scientific computation. I don't know. I haven't really run those. But for these kinds of codes, it doesn't bite. Okay, this is disabling the virtual iCache from the enhanced machine, and then incrementally on top of that, disabling the virtual data cache. So the green envelope is enhanced machine minus the virtual iCache, and the red envelope is enhanced machine minus both the VIC and the VDC. So you would expect a cumulative performance degradation. And so the lack of the virtual iCache degrades performance on the order of 0 to 10%. Again, male with a restricted REI is not helping much. Because it's flushing the virtual iCache all the time. And then the incremental performance degradation of the virtual data cache is one. Now, unfortunately, it's not really as simple as this, because just this element here is not necessarily indicative of the effect of the virtual data cache. It's really only indicative of it on a machine in the absence of the virtual iCache. So you really, to really look at this independently, you'd like to look at just enhanced minus the virtual data cache. But cumulatively, the two caches degrade the performance. Not having those two caches degrade the performance by 10 to almost 20%. So they're worth thinking about. But it would depend on both the economics and the complexity of the given situation. And here is the effect of serializing the auto-increment decrement specifiers, and then on top of that, serializing the indirect specifiers. If that specifier handling is not present in the enhanced machine, then they just stall waiting for the previous instructions to complete. So they don't have to worry about any interlock between memory or any interlocks on registers, synchronizing the register update. And what also means that you don't have to keep an R log or update the copy of the address registers when you have to back up. So in any case, the performance degradation here varies 5 to almost 25% without both those features. Clearly, not having the auto-increment decrement hurts a lot. In fact, maybe the solution would be to try to find an intermediate solution, both between adding the complexity I mentioned earlier and just serializing. I did look at the traces to see if maybe making somehow a special case out of the stack pointer would buy you most of it. But some of the traces do auto-increment decrement on registers beyond the stack pointer. Not much auto-decrement, but almost always the auto-increment is specifier references a number of other registers in addition to the stack pointer. And this slide reflects removing the virtual iCache from the enhanced machine, and then incrementally removing actually that should be E, removing the virtual iCache and the branch target buffer. Again, the branch target buffer with 8 bytes of the target iStream for branches in the branch history table. So in fact, that's actually acting for you like a cache of the sorts. If you didn't have that, you're going to have to wait a minimum of 2 cycles to get the new stream out of the virtual iCache, possibly longer if it's an iCache miss. If it's an iCache miss, you're going to be waiting anyway, because you're going to expire those 8 bytes pretty quick. So performance degradation here, not having it for the VIC in isolation, it looks on the order of 5 to 10%, 10% in most of the traces, and then incrementally removing the branch target buffer drags you down to, you still have branch prediction, but you don't have the branch target buffer, pulls you down to 50 to 20% range. This particular slide, it may be a little bit confusing. There's now 3 experiments, performance results on this slide corresponding to the enhanced machine without the virtual iCache, and that is the crosshatch set of lines that are going upwards. They're starting from 0. The crosshatch lines going downwards, this set here is no branch target buffer, and this outer envelope is neither the VIC or the branch target buffer. So the only point of this was that looking at now you can look at the envelope of the intersection between the benefit is provided you singly by the VIC or singly by the branch target buffer. And what you see is that not having the virtual ICAPS, which is the red upward slant, penalize you more, give us a performance reduction, penalizes you more than in isolation than does not having the branch target buffer. So if one had to make a choice between the two, it probably makes sense to go with the virtual ICAPS. Okay, this slide looks at no branch target buffer, and then incrementally. So in this case, we have branch prediction. This is the white portion. The branch prediction, but no branch target buffer means we're going to have to wait a couple cycles at minimum to get the new stream. And the outer envelope is no branch prediction, which means also no branch target buffer. So the penalty for not having the branch prediction is quite severe, because now it means that for stuff like bit branches, loops, and condition code branches, when condition codes aren't valid, which is almost all the time, you have to wait for previous instruction to complete, and that drains the pipe, which is going to degrade performance in the order of 20 to almost 45%. So probably, certainly it is the case that the branch prediction plus the target buffer, branch prediction in itself is probably the single most useful thing. Now, it may not be useful if you have a long tick cycle with very few pipe stages, because now you're not going to be waiting as many interval cycles. But in fact, branch prediction didn't buy you quite as much as this in the long tick model, because the pipe was not as deep. It buys you quite a bit more here. Now this is that VBAIK machine that I've got on three different basic enhanced and the design pointer. Basically, this is the machine without the length specifier table and without memory data forwarding. It's also without a couple other minor features. But it does have, take the basic machine, add the branch history table with the branch target buffer, add the virtual line, cache, auto increment, decrement, and indirect. And so each of these segments then corresponds to the performance improvement on top of the basic machine of adding incrementally BHT and then BHT plus the virtual caches, and then adding the auto increment decrement feature, and then adding the indirect specifier processing. And in fact, one might almost argue that adding the support for the indirect address is incrementally not worth it. It does add a fair amount of hair, and if not having it would reduce that, then it's probably worth skipping. So the performance improvement of these combinations over the basic machine is, the basic machine, bear in mind, does have 16 tags. It's not a serialized machine, but it doesn't have these other things. And so the improvement is 50 to over 100%. And just to contrast that with the enhanced machine, which has all the features on it, the incremental basically, so this the green envelope is the design point, if you will, and then the incremental, the red is the incremental improvement by adding those other features like DST, memory data forwarding, a couple of things. And as you see, it doesn't hurt you too much not having it, and it sure does yank out a fair amount of complexity. This slide is intended to illustrate the impact of having to flush the cache, or contact switch frequency, if you will. So now we're talking just about the VBAIK machine, design point machine, and then only varying the flushing. And so if we flush, and again, this is performance improvement over the raw basic machine. So the design point machine with a 1K flush interval only improves the performance up to a certain amount. Flushing less frequently every 2K, and then finally the outer envelope is not flushing the caches at all. That's not strictly true, because REIs still cause the branch target buffer and the virtual iCache to get flushed when they're detected. And so mail is down at the low end of this thing, as are some of the others which have more frequent REI instruction. So the mistake of not flushing the cache at all is probably a serious one. I in general have been flushing it around every 8K instruction, and that is probably optimistic. Maybe 4K is potentially a little more reasonable in terms of measurements made by Doug Clark and Jay Grady. This was, I mentioned the fast instruction parse, which was just done as an experiment to see what the effect would be in terms of potential performance gains. And in isolation, so these are features added to the enhanced machine. Adding the fast instruction parsing alone buys you 5 to 10% less in some cases. So probably not in isolation. And then as an experiment, it was interesting to take the enhanced machine and disable the address register interlock check, and then also disable cache flushing. And I think in this case, even the REIs didn't flush the cache either. That was turned off. So mail moved up as opposed to being almost consistently the low performer. It's now somewhere in the middle. So there's potentially, in this idealistic world, which is not achievable, there's potential performance gain of on the order of it really varies all over the place, doesn't it? Up to 50% if you never had any address register interlocks, or you could devise a mechanism such that they never occurred, which the DST was an attempt to at least set them aside. But it's clearly no substitute for not having them, because ultimately you're going to have to wait until it gets unlocked, and then the specifier is going to have to proceed from AD1 while the E0 command, which needs the data, is sitting down in the E-box waiting for it. Clearly, one of the ways to avoid address register interlocks clearly is to have the compiler schedule the code in such a way such that it doesn't happen. I don't know how practical that is for VAX. It is certainly an idea being exploited heavily in reduced instruction set computers with larger numbers of registers. And no cache flush is also an impractical proposition. Well, no cache flush corresponds to really having a fast memory. Just to give you a feeling for how the performance of the traces varied, we ran the whole traces. In some cases, took 10 or 12 hours to run some of the longer traces. And every 40,000 instructions, we measured the TPI for that particular 40,000 interval. Now remember, we don't execute all the instructions, and so some number less than 40,000, probably on the order of 35,000 or so instructions we actually execute somewhere more. So the average TPI, again, this is the design point, varies in the vicinity of around 5 ticks per instruction, a little less in some cases, a little more in some cases. And there's a couple other, I think they're included in the slides there, a couple other examples for the other traces of the variation in TPI at different points inside the trace. Let's, for a minute, my slides are out of order. I don't really remember where the hell this one was. But this is basically try to feeling for where in this space we're talking about. So it's a chart of ticks per instruction. A family of curves with a given TPI attached to the left of each curve. And a given cycle time is the x-axis, and the performance times 780, where 780 is half a MIP, or 10 TPI is assumed. So we have 780 half a MIP, half a MIP. So this corresponds to some envelope of performance. Now for this shaped area corresponds to long tick, and this corresponds to the short tick. And the question, of course, one wants to ask is the short tick demonstrably better than the long tick? Now there is a portion of the region that is better, but it's not clear. Certainly overall, it's not clear. And in fact, where you are in terms of TPI in this dimension is going to be a function of the given trace you're running, because given the instruction stream does different things for different regions of a trace or different applications. It's also going to be a function of in fact, the various feature set. Both long tick and short tick had a combination of enhancement features one could add and subtract or remove. And depending on what set has been selected, you're going to be sitting somewhere on that TPI line or in the vicinity of it. And the width dimension is basically cycle time. Again, the argument being that the long tick cycle time is roughly twice the short tick cycle time, in the sense that there are approximately twice the number of gates per path, per pipeline stage in the long tick than in the short tick. So in this case, we've taken, I think it was 15 to 20 nanoseconds, and here we've taken it 30 to 40. So the short tick is somewhere in this space, and in fact, what we just saw was that it's somewhere in the vicinity of the 5 PPI line for one of the machines. In fact, I do have some slides trying to compare short tick for long tick, which...
Dave, can I
Yeah.
ask you a question about that slide? There, before you were talking in terms of gate delays rather than a specific cycle time.
Right.
When you have these cycle times, is this comparable to the cycle times you would achieve with 780 generation logic?
Oh,
Because
no,
of
no,
your
by no means.
architecture,
Again, you
or-
have to go back to, ticks per instruction, or rather gate delays per cycle, which is, I think it was in the order of 10 to 12 or so for the short tick. And then we're making, some estimate about technology in the future, gate array technology providing you this level of performance. And I would hope that one could get somewhere in the range of 15 to 20 nanoseconds for next generation gate arrays for 10 to 12 gate delays. And so that is, we're assuming future technology for both of those.
If you just talk in terms of an architectural improvement, in other words,
Right.
not also a technology improvement,
Right.
do you have any feel for what kind of comparison with the 780 you would make for these models?
I don't actually have a number. Kane and I, a while back, decided that gate delays per instruction is an interesting metric. Because a larger number of gate delays per instruction for one machine, say you've got, well, let's stay within a single technology as opposed to considering MOS versus bipolar versus ECL versus TTL. If you're spending on the order of the same amount of money in gates or overall hardware cost, because you may want to make a disproportionate split in terms of RAM versus logic, then gate delays per instruction was the closest thing we could come to some sort of architectural independent thing. In fact, the TPI is more somewhat a structural performance measure, and cycle time is somewhat of a technology measure, but in some sense it depends how many gate delays you have per cycle. So getting to gate delays per instruction may make that a little more independent. We did do some computations, and we did conclude that the long tick model, this was just the long tick model, and I'd sent it up to the short tick model, are somewhat better in terms of architectural parallelism, if you will. But those I'm not prepared to stand behind those numbers, so I haven't put them in a report or made a slide up about it. One of the problems you have is what's a gate delay and what's the time for a gate delay. With MSI logic, how many gates are in a 200 nanosecond 780 cycle? Are you going to call a gate delay 5 nanoseconds? We did, but it's not clear that was fair. So,
Given what you know now, what should be the long tick, short tick?
I do have some comments about that, and I do have a bias toward the short tick, but for a variety of reasons which are included in the slides. And as a matter of fact, I think I would head right into those slides now, although there is a... Well, we have a choice. Should we talk about unsupported instructions and a compensation figure for them, or should we talk about short tick versus long tick if I'm going to finish in 10 minutes?
The latter.
Short tick versus long tick?
Yes.
You don't have to. You can take an extra 5.
Well, I suspect we'll end up taking that anyway, than even only doing one, but, comparisons are, as you probably would have guessed, difficult, crude at best, because the question you're going to ask is how do you know between the two designs without actually doing some detailed logic design of most of the parts of the machine, whether in fact you've spent an equivalent amount of hardware in the two design proposals. So initially we will take a crude track at this, comparing the two enhanced featured versions of both long tick and short tick, and then we'll pull out some features out of both of them and make a hand-wavy judgment that they're on the order of comparable, and then do that. So if you look at so the enhanced version, here's the long tick TPI down this column. Also, for this same set of traces, in order to make the comparison somewhat realistic, some of the instructions which the long tick model did, we filtered out of the traces that the short tick model doesn't, so that we didn't bias the. So basically, we ran the same traces through both models, even though the long tick model could handle some of the instructions. And the short tick TPI is down that column. I think you have this slide varying 3 to 4. So the short tick to long tick ratio is shown there in terms of TPI. Now, if you make the assumption, again, this is why the argument gets somewhat hand-wavy, that in fact the cycle time ratio between the two is a half. The short tick is half the long tick, as based on the fact that we believe half the number of gate delays per cycle are required. But again, without doing detailed logic design of all the parts of the machine, it's not clear that is a legitimate claim. So there's boatloads of caveats here. But in any case, if you accept that, then the performance gain of short tick over long tick is on the order of 10 to about 32% for comparing the two enhanced machines. Also, these figures out here on the left, on the right, the frequency of occurrence of REIs, in the sense that every 79 instructions we have an REI instruction for mail, and on the order of every 400 or 500 we have one for the directory trace and the EDT and link traces. And then these are here on the right are the frequency of occurrence of the move to processor, move to and from processor register, and those are bad ones because they serialize the pipe too. Now, one could probably be more sophisticated. I've just chosen to serialize the short tick pipe when it sees one of those because I don't know how it's going to affect subsequent instructions. But if one was somewhat intelligent and could decide this one is not going to hurt other instructions in terms of side affecting their execution, then you might not have to serialize every one of them. So the point is, high frequencies of these also degrade the performance of the short tick model.
That's just like the cycle time is
A factor of 2.
long. Your comparison is fairly sensitive to that, since judging from the ratio column, if it appears that it turns out to be 1.7 instead of 2, it's essentially no gain.
Right.
Okay.
Right. That's right. Oh, and also in this case, there was no cache flushing for either of the models, since the long tick model did not periodically flush the caches. And I wasn't about to go change the long tick model to flush the cache. So now we try another hack at comparing the two. This time we'll take, see, the long tick model had 2 address generation units and was able to decode 2 specifiers in a cycle. And now we're going to say, okay, you only get 1 address generation unit instead of 2. Because, in fact, the extra address generation unit did not significantly affect the performance because there are a lot of situations when you couldn't use both in parallel. For example, if you had an odd number of specifiers, only one would get used at the tail end of an instruction. If both specifiers were memory reference or auto increment decrement, they would have to get serialized because there was only one memory path. So in any case, 2 AD units did not help tremendously. There's going to be no RSP stack. There wasn't any here. No memory data prefetching, which was used only for index mode specifiers and only really helped loop code. No read-write pending stacks in the main cache. That would allow you to set aside a miss and, or set aside a write and let other requests move through the cache, but they'd have to be interlocked on any potential write address. And a 4-entry buffer was added to the, specifier buffer was added to the input of the address generation unit in the short-tick model because the design point model of the enhanced machine has that feature. So what that means is that if you've got a register interlock problem on generating an address, you can possibly have extract and parse 4 more address type specifiers before it has to stall because it has no place to put it. Okay, the changes on the enhanced machine were no target address calculation and extract for jump and JSP. That is, no displacement off PC detection for jump JSP type instruction. Instead of 1 cycle for decoding the index specifier plus the base specifier, it takes 2 serial cycles to process those. No delayed specifier table and no memory data forward. Now, if you compare these two, again, you have short-tick TPI and long-tick TPI, and the percentage gain is quite a bit better, again, assuming that you've got a factor of 2 to 1 in the cycle time. I didn't compute the ratio here, but it now gets up to as much as 40 or 50% for 50% for length, and it's as low as 20% for chariot. Now, the only question one has is how fair is this comparison? First of all, is the cycle time actually a factor of 2? Have we pulled out hardware out of the machine so that between the two models, so that have we spent roughly the same amount of bucks? Who the hell knows? And that's why comparison is going to be difficult unless you want to actually, spend a fair amount of effort going down trial design path. So this gets into some, because of the caveats, I just have some observations. I don't know if it's worth really going through these. One can always read them in the slides, contrasting the different approaches. But I guess I want to argue a few things. I believe that designing the time sequential segments in a pipeline is easier to manage than parallel ones. An example is the 2 AD units, parallel AD units in the long tick versus the serial unit in the 2 pipe stages in the short tick. For example, and you have less hardware is one example. Only 1 copy of the registers in the interlock logic instead of 2 copies, 1 in each AD unit. You have only 1 address adder, and you have no sequencing of discharging or processing when they either do their side effect thing or they want to reference memory. Because ultimately, if they both want to reference memory, one's going to go in front of the other. And what's more, in fact, the bandwidth through the short tick model, you could argue, might be in fact somewhat higher because in the long tick model, one of those stages is going to be idle for the odds, numbers, and specifier case, add long 3 kind of thing. Because the long tick model does not attempt to do the last specifier of one instruction and then in parallel with the first specifier of the next. Okay, a very disgusting possibility. So that was that comment there. Also, the short tick design has the potential of giving you twice the memory bandwidth than the long tick design, but in order to get that bandwidth, you have to be able to carve up your memory system into finer stages, and depending on how you design it, that may or may not be possible. Now, the way we tried to make it possible was, in fact, having this virtual data cache, with the first stage being a semi-custom tag store CAM part to do the lookup in 1 cycle and the error checking on protection violations and whatnot. And then a second cycle with a small number of fast RAMs to cough up the quad word that contains the data. Having a faster cycle gives you a finer time resolution to release stalls and deal with interlocks, and it also lets you get a higher throughput for these single cycle execute instructions, which are very popular. This is, of course, only true if you have this result discharge unit. For something like even a single cycle execute in this model, it still takes 2 cycles because it takes a second cycle to discharge the result depending on where the hell it's going. Now, if you have the second, you do the alley function in the 1 cycle, and the next cycle you try to figure out where the hell to put it. And if you had that would be fully piped. It'd be interesting to try that, see if it really buys you much performance. That was something I didn't get to. Also, one would argue that keeping the functionality in the pipe stage simple, i.e. not much logic, front to back in the pipe stage, potentially makes it easier to design because there isn't as much opportunity to do crossways, interconnections of logic. That's a very hand-wavy argument, but fundamentally, if you've only got a few gate delays, 10 or 15 gate delays to do something in, you can't get too fancy about how you do it. Although it potentially that does hurt you. We'll see that. Yeah. I was going to say that the short tick approach gives you greater performance leverage if you get less than 6 TPI. If you looked at those curves, you get less than 6 TPI. A unit decrease in terms of a nanosecond in cycle time buys you quite a bit more. But of course, the other side of that is if you get bagged by technology or packaging or something, the performance penalty is going to be more severe. So in fact, undoubtedly, taking the short tick approach from looking at it from that standpoint, it's a higher risk proposition unless you have very tight control over the packaging, partitioning, and technology performance. So that's among our drawbacks is the physical design and performance of the logic packaging.
Dave?
Yes.
You might get a slightly different insight on that last point if you plotted the performance axis on that graph as a logarithmic scale. It's sort of implied by the fact that you're saying times 780.
Right. I did plot it in logarithmic, but it was an interesting graph, and I have difficulty thinking in terms of logarithms on the x-axis. I did, in fact, take a little poll of a couple of people, said, which do you like better? And they all liked the linear axis better.
It looks great when you're shooting up there. It just doesn't mean a whole lot.
Well, it means it's a point of leverage, which you may or may not be able to exercise. Or you may, in fact, get bagged by. Right? If you're up there, say you're at 20 nanoseconds or 15 nanoseconds, and all of a sudden the drivers on your chip go to hell, and now you're out at 25, that's going to be a serious pain.
Well, it looks like a lot of distance on the vertical axis, but of course the ratio is no bigger there than it was down here where it was a smaller distance. So, yeah.
Are you saying that if you took the same percentage performance hit in the short and versus short tick and long tick, that your performance will go down by the same amount versus taking a constant hit as a function of some surprise? There's getting hit by 5 nanoseconds with a long tick is not going to hurt you as much as getting a 5 nanosecond hit by the short tick. Okay, I'm this.
Because you don't get hit by 5 nanoseconds. If you have twice as many gates, the manufacturer changes the gates, you get hit by 10 then.
Right, at which point it's a percentage hit and not an absolute hit. I appreciate that.
Okay.
But some of the other difficulties are inherent in the design in the sense that you've got less time to do things, which means you've got less time to propagate pipeline stalls backwards, as an example. You've got less time to figure out that oh my, you've got to stop, and now you've got to tell the guy behind you to stop. And so one way to potentially manage this is to provide additional buffering so that you have an extra cycle or two of empty space in which to dump something before you in fact lose data. But that's of course just added complexity. Also, clock skew is more difficult to control here, or clock skew must be more carefully controlled than it is in the long tick. An example, I guess clock skew on Venus is something on the order of, I don't remember now, but it was something on the order of 5 to 10 nanoseconds or something. It was a fairly gross number. Now clearly, if you kept that same clock skew going to short tick, that's a very bad business, and that may be that may be the hardest thing to manage more than anything else. Also, the logic design itself is more critical because you have more gates and you have to more carefully manage the partitioning of the design and manage more carefully the number of logic levels because you have less time. An extra gate delay among friends may or may not hurt you too much in a long tick design, although in some cases you get the impression that's the way the designers look at it. But clearly it's much more carefully controlled. An example would be the Cray 1 design in which a unit gate delay approach to managing time was used, in the sense that every cycle has 8 gate delays, no more, no less. And if you go out across the twisted pair connecting modules, every, I think, foot and a half of twisted pair you used cost you another gate delay. And clearly that's far more sophisticated management and far more simplistic management of timing than, for example, Venus was doing. And that is it for that. And I have in fact gone over, so you won't get to listen about the unsupported instruction caveats, but you'll see that in the report. Are there any other questions? Yes.
Where do you go from here?
Oh, I did have a future work slide. I wasn't going to do it, but what the hell. This is stuff that ought to get done in the future. More work ought to be done. In particular, some logic design studies of a couple of the units, extract and E0, which are the two most complex units, ought to be done to really get a good feeling for whether or not the principal functionality of these units can happen in a single cycle. Those are the two most complex units in the machine by a long shot. And that hopefully would let you estimate a cycle time. And another thing has to be done in terms of, I mentioned the business of propagating stalls backwards. And careful thinking up front has to go into a mechanism for pipe segment control so that you don't get bagged by it later on in the design. Other work, especially related to compiler optimization and scheduling of code, might be warranted. In fact, you could also try to influence the compilers to stay away from some instructions which you don't do particularly well and don't really want to do particularly well, or stay away from some addressing modes, like auto-increment specifiers, increment decrement, or indirect addressing. A lot of work could really be done in that space. It's not clear anybody's going to do that. I guess Venus people are getting together with the compiler group, Fortran compiler group, and Squidbook to try to influence some code generation.
Kevin Harris is doing some work on that now.
I don't know if
No, he's in charge of Fortran.
I see. Also, ought to look at more traces than what I've looked at. I think I've looked at a variety of traces, but clearly you'd like to go off and look at floating point computations other than just little floating point loops. I have a bunch of traces of floating point loops, but I don't have larger, more sophisticated applications. And much as I hate to admit it, you might want to go look at COBOL and look at the decimal instructions, which I certainly have ignored here. And continuing to explore the design space, there's a list of random things that ought to be done. I think you can make this thing somewhat simpler, especially the memory data interlock stuff. Now that specifiers are in order, and it turns out that memory data forwarding doesn't buy you anything, you can instead rip all that stuff, the cams, out of E0, and instead put a little cam up in the virtual data cache, which keeps track of outstanding writes, or actually it would keep the low 9 bits of the virtual address, which doesn't have to be translated, and in fact only check the upper 7 of those low 9 bits. And if a read behind a write references that particular offset in a page, then you stall it until that write completes. And I haven't tried that. That was suggested by Trigby, and I suspect it'll work very nicely, but I haven't tried it to see in fact how well it works. So there's some things like this that I think you can continually evolve this and try to make it less hairy.
Are you going to do any of those things?
I don't think I'm going to be doing any of those things. It's not clear who's going to be doing any of those things. We thought at one time that Fernando Colon Osorio, I think that's how it's pronounced, was interested in continuing some of this work, but he, I think, his interest has changed a little bit. And so Kotok is manager of structural AD, if you will, in Marlboro, and he owns basically the project. He has to decide what he wants to do with it. I think he thought Fernando wanted to pick it up, but I guess maybe Fernando wants to do something else now. I myself am going to go off and look at risk machines, so I guess I won't be doing anything with it. The people in Hudson have taken a copy of the simulator and decided to use it for a first cut at looking at a follow-on, I guess it's called the Rigel project, I think, to V11 to see, just to play games and see what they do. Basically, I think they're looking for 10x, and I think they could get 4 4X from technology, was it? And they wanted to get the rest of it from structural improvements. And so they just grabbed that, and we're going to hack it out to try to fit it within a conceivable partitioning on a collection of MOS chips to see what might come out of it. I don't know what's beyond that. And they've only started doing that, so it'll be a few months before they decide whether or not this is a possibility or something else should be done. Is that it? Well, thank you for coming.